Welcome to today's video. In this video, we're going to discuss limits of convergent sequences and methods to obtain them. So this is called limits of convergent sequences. And we'll start with a simple theorem that tells us how to construct new sequences from sequences that we already know. And of course, simple operations that you can do with sequences is you can add sequences, you can multiply them, you can divide them if the denominator is not zero, or you can apply other operations to them. And the question is, if you use convergent sequences for that, is the result also convergent? And what is the limit of that? And the answer is, as you would hopefully expect, in general, yes, the result will be convergent, and the limits can be obtained from the same operation. So let's write this down more precisely. So let's say we have two convergent sequences. We'll call them AN, N0, and Bn, N0. Be two convergent sequences. And let's say their limits are A and B, respectively. Then the following holds. We can add or subtract these two sequences, and the result is again convergent. So the limit of AN plus Bn is A plus B. And if I subtract those, the limit of AN minus Bn is A minus B. I can also multiply those two sequences, and if I do that, the limit of AN times Bn will be A times B. Of course, I can also divide them, but I have to make sure that the denominator is not zero. So if Bn is not zero, for all n in N0, then I can define a limit, or I can define a sequence AN divided by Bn, and that is convergent and has a limit of A over B. And of course, to hold, also B limit must not be zero. So it's also an important thing to add. For an operation that I also need sometimes is to apply the absolute value. And of course, also that does not hurt sequence convergence. It may change the limit, of course, to the absolute value, but that's it. So the limit of the absolute value of a sequence AN is the absolute value of the sequence limit. One other operation that we'll need frequently is taking the square root. And we can do this if a sequence is non-negative. So if AN is non-negative, for all n in N0, then the limit of the square roots of the AN is the square root of A. And of course, I implicitly assume that A is non-negative as well. We'll discuss that property a little later, but that's indeed true. And finally, I can also compare sequences. So if one of the sequences is larger or equal to the other one, at least from a given index on, then the same thing will hold for the limits. That's the last property in this theorem. So if there exists some capital N in N0 such that AN is less or equal to BN for all indices that are at least capital N, then also the limit will obey to this inequality here. As a little side note, if AN is strictly less than BN, then that also means A is less or equal to B. So please notice the equal sign here. The limit may still be the same, even if all elements have a strictly less than relation. The limit might not be strictly less, but it might be the same. And another remark, what this theorem says in particular is that you can apply linear combinations to sequences. And if you combine convergent sequences, you will again get a convergent sequence. So in other words, the set of all convergent sequences is a vector space. So just as a little remark. The set of all convergent sequences is a vector space as linear combinations do not change convergence. Okay, so these are very basic properties of sequences, and that means you can construct many sequences from very simple sequences, but just adding, subtracting, multiplying, dividing them, and you'd automatically get convergence for these newly constructed sequences. Another theorem that is sometimes important is one that tells you that a sequence has a limit without actually giving you that limit. That's a two-part theorem. The first one simply observes that every sequence that is convergent is also bounded, because, of course, the sequence will eventually be very close to the limit, and it will not be able to surpass every possible bound because it doesn't get away from that limit anymore. Of course, in the beginning, it may make jumps, but those are limited by the elements themselves if necessary. But it cannot jump arbitrarily high or arbitrarily low because it will get closer and closer to that limit. So that means, obviously, every convergent sequence is bounded. And remember, a sequence that is not bounded and tends to infinity, we don't consider that a convergent sequence. This is a divergent sequence. What is more interesting is the reverse of that. The question is every bounded sequence also convergent? And the answer is, of course, no. Have a look at the sequence -1 to the n that alternates between +1 and -1. That is certainly bounded, but it's not convergent. So boundedness alone is not sufficient. But if you combine that with monotonicity, then it turns out that is sufficient. So if a sequence is bounded and monotone, then it is convergent. And that's the important part of that theorem. If a sequence is bounded and monotone, then it is also convergent. And let's have a look at an example of such a sequence to see how we can apply this theorem. One setting where this is often useful is if we have sequences that are defined recursively. So we consider the following sequence: an and 0 defined recursively as, let's say we start with a0 equals 2, and then we define an by the previous element by saying we take the previous element of a sequence, we divide that by 2, and we add 1 over an minus 1. And we do this for n greater or equal to 1, of course. Then the first thing that we can note is that this sequence is bounded. It's actually not that easy to see, but an easy bound to prove is 2, and I'll show you how to do this. So let's first have a look at an squared. We square the sequence. We'll see in a minute why that makes it easier. So what happens if we do this? Well, we have 1 over 2 an minus 1 plus 1 over an minus 1 squared. And we can, of course, express that explicitly as an minus 1 squared over 4 plus 2 times 1 over 2 times an minus 1 times 1 over an. So these two cancel out, and 2 times 1 over 2 also cancels out. So the factor in the middle is 1 plus 1 over an minus 1 squared. And that 1 here is what makes it particularly interesting, because if we now go ahead and subtract 2 here in the beginning, and of course we just carry that through like this, then we can simplify this to obtain an minus 1 squared over 4, and then plus 1 minus 2 will become minus 1. And we just keep the last summand here. And you'll immediately notice that is almost the same as this formula here, but with a minus instead of a plus in the middle. So again, we apply one of the binomial formulas to see that this is actually the same as 1 over 2 an minus 1 minus 1 over an minus 1, sorry, squared. So what does that mean? Well, this is a square of something, so that is sure to be non-negative. And what do we get from that? Well, if we have a look at the beginning and at the end, we can see that this means an squared minus 2 is non-negative. So in other words, an squared is greater or equal to 2. And that means an is greater or equal to the square root of 2, as obviously the an's are non-negative. So taking the square root will result in a positive an here. Okay, so we have bounded the sequence below. Another one thing that we need is part 2. We prove that the sequence is decreasing. And that means the values of the sequence always lie between 2, that's the first element, and square root of 2, that's the lower bound. So the first element is an automatic upper bound if the sequence is decreasing. And that's what we've seen now. So the sequence is decreasing. And to see that, let's have a look at the difference of an and an-1. Now we know by the recursive formula an is equal to 1 over 2 an-1 plus 1 over an-1. Right, so this here, this is an minus an-1. So what we have is half an-1 minus an-1. So that's equal to minus 1/2 an-1. And that second sum, and we just copy that. And then let's see, we can put this on one fraction. So we have denominators 2 and an-1. So the common denominator is 2 an-1. And then we get minus an-1 here times an-1. So we need a square here. And a plus 2 from that expression here. So what do we see here? Well, we know that an squared is bounded below by 2. So this expression here, that surely is less or equal to minus 2, because an-1 squared is at least 2. That's the lower bound. So minus that expression is less or equal to minus 2. So we have a number that is less or equal to minus 2. We add 2. That means we can get something negative or at most 0. And again, this denominator here, that's non-negative, so that doesn't influence the sign. So we can be sure that this is less or equal to 0. And let's take this together. That means this difference is less or equal to 0. So all in all, an minus an-1 is less or equal to 0. That means an is less or equal to an-1. So, in fact, the sequence is decreasing. So what we have is an is contained in the interval from square root of 2 to 0. So square root of 2 is less or equal to an is less or equal to a0, which is 2. So it's bounded. And it's also decreasing. And that means by the theorem, an is convergent. And now once we know that, and only then, we can also compute the limit. Because for the limit, of course, the recursion formula also has to hold, right? It holds for all of the elements, and those get closer and closer. So, of course, in the limit, the formula will also hold. As the recursion holds for the limit, let's call that limit a. We get a is equal to a over 2 plus 1 over a. Well, let's multiply that by a. Then we get a squared equals a squared over 2 plus 1. And that means a squared over 2 is 1. And that means a squared is 2. So what we get is, as we know that a is positive, a is the square root of 2. Right? So this sequence converges to the square root of 2. And this is something that is not very obvious from the beginning. It's not even obvious that the sequence converges at all. So the value of that theorem is to give us convergence, and then, only then, we can use this recursive definition to obtain the limit. If the sequence diverges, that recursive definition might still have gotten us something useful, but it would not have been a limit. So that can only be used if we know that the sequence is convergent already. So that completes this example. In the next theorem, we're going to have a look at 2 more sequences that appear very often, that we've seen already, in fact. I'd just like to collect these results here, so we all have them neatly in one place. We first have a look at the geometric sequence. So that is part 1 of the theorem. The general geometric sequence. That's a sequence AN, N0. Let that be defined as AN equals, let's say, some A0 times Q to the N for N in N0, for some initial value A0, let's say that value is in R and not the number 0, because that would make for the constant 0 sequence. That's not very interesting. And then Q is also a real number. For example, we've seen the sequence 1 over 2 to the power of n. So Q is 1 over 2, A0 is 1. That's a geometric sequence. And what we know about the convergence of that sequence is the following. The limit of AN. So if we take a Q that is strictly between -1 and 1, like 1 over 2, then of course the value decreases, or at least the absolute value decreases. It gets closer and closer to 0. So the A0 does not matter, as the Q to the N part converges to 0 already. And that means the whole limit will be 0 if the absolute value of Q is less than 1. So Q is between -1 and 1. If Q is equal to 1, of course, then we just have a constant sequence that is equal to A0. And if Q is greater than 1, then Q to the N will increase. So we get a sequence that is unbounded. That means we have infinity if Q is greater than 1. And A0 is positive. If A0 is negative, we'll of course have minus infinity. And furthermore, if Q is less or equal to -1, then we will also get some alternating behavior. So the sequence values will increase, or at least stay at A0, that is not 0 then. And they will also alternate, so we will not have convergence at all, and we will also not have a sequence tending to plus or minus infinity. So for Q less or equal to -1, the sequence is divergent. So this is a geometric sequence. Another sequence that often appears is the so-called harmonic sequence, or generalized harmonic sequence. And that is the sequence AN. This time we use the index at n only, not n0. We have to exclude that. And let that be the sequence defined as AN equal to 1 over n to the power of L for some L in the integers, possibly negative integers. Then if L is negative, of course, that's the same thing as n to some positive power, and that is obviously a divergent sequence. In the other cases, it will be convergent. So then the sequence is divergent for negative L. And for the other cases, let's have a look at that. So the limit of AN is, well, if L is positive, then we have 1 over n to the power of L. And as n increases, of course, that fraction decreases, so that gets closer and closer to 0. We've seen 1 over n already. Of course, 1 over n squared, 1 over n to the third, and so on. Those behave in the very same way. So what we get is the limit is going to be 0 for positive L. If L is 0, then 1 over n to the power of 0 is 1 over 1. So that's a constant 1 sequence. And of course, the limit is then also 1. And we already said in the case of negative L, the sequence is divergent. But as n is still positive, it does not alternate. There's no jumping around, but instead the value grows and grows and grows. So it's going to be unbounded. It's going to tend to infinity for negative L. So that's the behavior of the harmonic sequence. Let's have a quick look at an example that shows us how we can combine our knowledge about these sequences and about the combination of sequences to get a limit of a more complex sequence. Let's have a look at the sequence defined as 3n squared plus 2n plus 1 over n squared plus 1. And what we want to do here is we want to rewrite this as a combination of sequences that we know. And in particular, in this case, the harmonic sequences are of interest. So what we'll do is we'll search for the highest power of n. In that case, that is n squared here and n squared here. So the highest power that appears is n squared. And we factor that out. So we factor out n squared in the numerator and also in the denominator. So we factor out the highest power of n. And what remains is, in the numerator, we have 3, of course. Then we have plus 2 over n and plus 1 over n squared. In the denominator, we get 1 plus 1 over n squared. And now you'll notice these are harmonic sequences. So we can cancel out the n squared, of course. So we have 3 plus 2 times 1 over n plus 1 over n squared. And we have 1 plus 1 over n squared. And that means both the numerator and the denominator are sums of convergent sequences. Yeah, this is a constant sequence that, of course, tends to 3. This tends to 1. Here we have harmonic sequences that tends to 0, and that also tends to 0. And here we then have a product of two sequences, the constant sequence 2 and the harmonic sequence tending to 0. So the product of those two tends to 2 times 0. That's also 0. And that means in the end what we get here is as n tends to infinity, this whole expression tends to 3 plus 2 times 0 plus 0 over 1 plus 0. And you'll note that the denominator here is not 0. So again, we have two sequences. The denominator is not a sequence that tends to 0, and it's not 0 itself. So we can fairly conclude that this sequence tends to 3 over 1. So the limit of an is in fact 3. Now, finally, to round this discussion of convergence and limits of convergent sequences, to round that off, I'll have two more theorems that we'll employ sometimes. The first one is called the Sandwich Theorem. And you see in a second where the name comes from. The idea here is you have three sequences this time. So let an, n0, bn, n0, and cn, n0 be sequences. And let's say we can compare those sequences, at least from a certain index on. So let n be a natural number, an index, such that an is less or equal to bn is less or equal to cn for all n that are at least capital N. So you could say bn is sandwiched between an and cn. And what makes this even more clear is the next requirement. And that says if an and cn are convergent sequences and converge to the same value, so that sandwich kind of gets thinner and thinner, then bn must also converge. So that's the idea here. If an, n0, and cn, n0 converge with the same limit. So limit of an is equal to the limit of cn. Then bn is also convergent with the same limit. Right? So what we have here is a setting like this. Let's say you have these two sequences here. Let's start with, let's say, an. An is a sequence below. So you have a sequence an that gets closer and closer, let's say, to 0. Let's say 0 is the limit. So this is the an sequence. Then you have the cn sequence. It's also getting closer and closer to 0. So that might be the cn sequence. And then the bn sequence is somewhere in between. And the idea is then that this has to close in on 0 as well, right? So this is the sandwich behavior here. So that, that sequence bn is sandwiched between c and a. We'll make use of that theorem later on in another video. And finally, one thing that also often comes in handy and is often necessary is to compare the growth of polynomials and exponential functions. And actually, we make use of that again in one of the following videos. So in more detail, let's say we have a natural number n. We have some very small number, let's call that epsilon, and some small positive number. And we define a sequence, the sequence an, defined as an is equal to, now we start with a polynomial in the numerator. So the numerator is of the form n to a constant power, and possibly summands of lower degree that do not really matter for the convergence. And the denominator, that will be not a polynomial but an exponential function. So that means we have some number, some constant number, 1 plus epsilon, possibly a very small number but above 1, greater than 1, and we take that to the power of n. So the n appears here and here. Then what this theorem says is, of course, both the numerator and the denominator go to infinity, but the denominator is much faster. Basically what that means is that the limit of an will be 0. So the sequence defined as an that converges with limit of an equals 0. So exponential growth always outgrows polynomial growth, right? So this here is, numerator is a polynomial, and the denominator is an exponential function, and that in the long run is always much faster, always grows much faster than a polynomial. So that concludes this collection of important facts about limits of convergent sequences. It's been a long video, so thanks for your patience. In the following videos, we'll again have a look at applications. We'll deal with the exponential functions, and then we'll switch our attention to series. And as usual, I hope I'll see you then.